Welcome, mathematicians. 2,300 years of calculus. That's the title that was suggested to me for this video by a student that saw a version of it 2 days ago, but I didn't have a recorder turned on. It was a live lecture in person at Catholic University, but it seemed like a pretty good catchy phrase for the title. 2,300 years. You think of calculus, something is about a little over 300, maybe 350 years old, at least the Newton and Leibnitz. But one of the points that I'm definitely making in this lecture is that a lot of the concepts of calculus go back way further than that. Euclid. I definitely want to start with Euclid. Let me zoom this in a little bit. Euclid flourished 300 BC. Really, one of the most the prominent early mathematician. Really, his Elements is kind of like the first math book. Certainly, one that's that survived to this day. And if you were to ask people what is Book 1, Proposition 47, it's this. It's Euclid's proof of the Pythagorean theorem that these two squares are equal, the sum of these two squares equal the sum of the area here on this square here. A squared plus b squared equals c squared. But if I were to ask you what is Book 12, Proposition 2, I actually did have someone 2 days ago who knew what it was. Yeah, Book 12, Proposition 2. Circles are to one another as the squares are on their diameters. What does that mean, roughly speaking? It means that you have a circle here, sort of, and the area of the circle. You also draw a square here. Draw a square. This is a square on the diameter of the circle. So the area of the circle is proportional to the area on the diameter. That's what he says, right? Circles are to one another as the squares on their diameters. It's actually interesting he didn't know what the proportionality constant was. That was Archimedes that figured out that this is, in fact, what in modern notation, the area of the circle would be pi over 4 d squared, because d is the diameter is twice the radius. Really it's the same as it's pi r squared, just that here we have the diameter. And that is actually kind of interesting that pi over 4, if we take a quick look here, what is pi over 4? Let's see what we got here. Pi over 4. 0.7853. 0.7853 pi over 4. Really what it's saying is in this diagram, this circle inside the square, the circle occupies about 78.53% of the area of the square, which is kind of an interesting observation and maybe even a more natural way to express pi, but I'll leave that up in the air. Anyway, what I want to really emphasize here is his proof method. He's basically saying that if the squares, or this is a very nice website, by the way, D. Joyce, English translation of all of Euclid's Elements. But okay, so if the square is if they're not in proportion, then there's going to be some excess. It's either less or greater than. And the first branch of his argument is that it's less. So we're going to construct an inscribed square. It's EKGH, and then we're going to bisect the circumferences K and Yeah, and bisect the circumference, and now we're going to turn the square into an octagon, and it keeps going down, and this is the kind of interesting phrase. By bisecting the remaining circumferences and joining straight lines, and by doing this repeatedly, we shall leave some segments of the circle which will be less than the excess by that which the circle exceeds. Yeah, it's basically a kind of like an epsilon delta argument from 300 BC. That we're just going to keep doing this. There's some excess. There's some, epsilon, or, in modern notation we say epsilon maybe. There's some excess, and by repeatedly bisecting the circumferences, we get denser and denser polygons. It's a square. It's an 8-sided polygon. It's a 16-sided polygon. It's a 32-sided polygon. Eventually, we will get to a polygon which is closer to the area of the circle than, some epsilon, and epsilon could be in any arbitrarily small number. That's kind of how we would phrase this today. But, let's look at the this is the less than branch of the argument, where we're constructing inscribed polygons. And then, now I think we're gonna do x. This is inscribed. I think we're gonna do x circumscribed polygons. If for the other branch of the argument, I think it'd be circumscribed polygons. These ones outside the circle. So really, the logic here is that if we have polygons constructed inside a shape, in this case the circle, then the area of those polygons obviously has to be less than the area of the circle. If they're circumscribed, if they're all, now the polygons are constructed outside the circle, then their area has to be larger than the circle. And if we construct a series of, put this on a number line, and we have, the smaller areas, and we can construct them for a whole infinite series, and we keep bisecting repeatedly, as Euclid said, until we get to some limiting value. And then we have the larger ones, the circumscribed polygons, and as they get denser and denser and denser, they also approach a limiting value, and that limiting value is the same for both of them. Well, then that limiting value must in fact be the area of the shape that we are approximating. And this goes back literally 2,300 years to Euclid. But like I said, he didn't know what the proportionality constant was. That was Archimedes. Archimedes is the one who figured that out. I think somewhere down here, so we see what his Archimedes principle, his screw, his claw, his heat ray, method of exhaustion. That is what this whole process is called. And here he is constructing an approximation pi. He finds an approximate value of pi that's pretty accurate, and he also proved the area of the circle is equal to pi multiplied by the square of the radius of the circle. This is his this is the particular property here, that the proof that I just lost it there, right there. The area of the circle is equal to pi multiplied by the square of the radius of the circle, pi r squared. So this is really one of the earliest theorems that we know who proved it. And the method of proof is, if we were to take this circle and we divide it up into pi-shaped segments, and we line all these pi-shaped segments up. Maybe I should erase some of this here. Let's get rid of this. Let's line up all these pi-shaped segments. And we're going to, what's the area of all these pi-shaped segments? Well, yeah, we do this for the entire circle. And as we make more and more, as they become thinner and thinner, as the total length of their bases here becomes approximately the circumference of the circle. So this whole part down here, in the limit, we would say today, becomes C. The heights of these triangles, again in the limit, becomes R, the radius of the circle. And then each one of the triangles is area 1/2 base times height, height being R. And as we add them all up, we can just factor out the 1/2 R, and the sum of all the bases is C. So we got 1/2 C times R, and then by definition, C equals either pi d or 2 pi r. This is really the definition of pi. It's the ratio between the circumference and the diameter, and we put that in, and we get 1/2 2 pi r. The 1/2 and the 2 cancel, and we get pi r squared. So we find that the proportionality constant here is pi, and up here the proportionality constant is 1 pi over 4. So that, like I said, this is in this whole method. That's like another example of the method of exhaustion, and that is the quadrature of the parabola. That's something that this is, one of Archimedes, famous accomplishments, that he calculated the area under a parabola, inside a parabola. I wrote an essay a number of years ago about, drew up a notepad a number of years ago about this. Which here we want to find the area, this green area inside the parabola, and to do that, this is Archimedes' method. We construct a number of these triangles, and because they all have equal base and height, they all have equal areas, and we're able to determine, therefore, that we want to take like this triangle up here, and we find there was 1, 2, 3, 4, 5, 6, 7, 8, and then this one here. What we're trying to do is trying to find this gray area here. We're trying to extend from this triangle, and we're bisecting it, and we're adding these two more triangles. We find that both of these are 1/4 the area of the triangle shaded in green. And then we keep doing this repeatedly, keep repeatedly bisecting and getting finer and finer approximations, just like with the circle. And now it's done with these triangles, and we add here's some notation using more modern notation to prove this. And finally, we get an infinite series. That each one, adding each new set of triangles adds area which is 1/4 of the triangles before it. So we got 1/4 plus 1/4 squared plus 1/4 cubed, and now we do a relatively simple calculation here to run an infinite sum. I said it here, it's a common trick for solving geometric series without really any kind of modern concepts of limits. But yeah, this is what Archimedes did. He did this calculation basically. He included the area of the parabola is 4/3 the area of the inscribed triangle. So for this one, the area of the green area, don't have a single triangle here. It would be this one. It would be this one here. This is the parabola. The total area in the parabola is 4/3 the area of this triangle, and these regions here are an additional 1/3. So this triangle plus an extra 1/3 gives us 4/3. So the area of the parabola, 4/3 the area of the inscribed triangle, which is correct. The method of exhaustion. We're exhausting a geometric shape. We're constructing really an infinite series of smaller and smaller geometric shapes that in the limit completely fill the geometric shape, and this is something that dates back to before the time of Christ. Anyway, and then here is, I think, a page about pi, and just I think I had this one here was just the question of just the history of the thing, and it certainly dates back to as we just said, Archimedes definitely found some really proved the pi r squared, area equals pi r squared. All right, so that's what they were doing in ancient Greece. Moving along, almost 2,000 years, Cavalieri. We're now early 1600s, so approaching the time of Newton and Leibnitz, approaching the time of the modern calculus. But this is the Renaissance. There are a lot of ideas floating around here about how to do these kinds of calculations, and this was, Torricelli. This guy, Torricelli, inventor of the barometer. He wrote a book in which he listed 21 different proofs of the area of the parabola, the quadrature of the parabola. 21 different proofs, I believe, is the number. I know two of them, and of course the third one is the calculus that had not yet been invented in the early 1600s. But this is Cavalieri's idea for how to do the quadrature of the parabola. So we take our parabola. This time we're going to compute the area under the parabola rather than inside the parabola, but it's basically, it is really the same. The difference is just subtract it from a rectangle here. And what we're going to do, Cavalieri's idea is we're going to add up all of these little line segments, or argue that kind of like the way in the pages of a book are all very thin, but they add up to the volume of the book. The idea here is all these little line segments add up to the area under this parabola. Well, what is the parabola? So we know it's, say, y equals x squared. That means each of these little lines is of height x squared, as we let x go from, let's call this a. As we just let x range from 0 to a, any one of these particular little lines is going to have height x squared. So somehow we're trying to add up x squared, an infinite number of x squareds, trying to add them up. How on earth are we going to do this? Modern, thought is like we immediately have, it looks like we're trying to add up an uncountable sum. This is really kind of, tricky to even define what this is, but Cavalieri's idea was, let's find something very similar to this that has a similar looking sum that we do know how to add up. And his answer was, we do know something similar, and that is a pyramid. Let's construct a pyramid. Take that out. Yeah, a pyramid. And it has been known since the time of Euclid what the volume of a pyramid is. It's 1/3 the area of the base times the height. And in this case, if we set the base equal to a by a, and the height is also a, then each of these little planes in here will have area x squared. As we let x vary from 0 to a as we move along the height of this parabola, let's say that this point here is x, then the area of this square is going to be x squared. So we're summing up x squareds here, and this is what we want here. It's very similar to what we're doing here. So Cavalieri's idea is that the area under this parabola must be the same as the volume of this triangle. The area of the base is a times a squared. So we get 1/3 a squared. The height is a. And yeah, this is 1/3 a cubed, which in fact is the correct answer. If we just to check this, let's take a look at the triangle here. The triangle is, area of this triangle is 1/2 the base times the height. Well, the base is going to be 1/2 the base, which is 2a, since it goes, let's see, let's just do a. Let's just do half of it, since that's all we're computing here. Is this 1/3 a cubed is just the right hand part of this parabola. So let's just do this part here. This is 1/2 the base, which is a. The height is a squared. So the area of the triangle is 1/2 a cubed. Archimedes showed that it's 4/3. The area of the parabola inside the parabola is 4/3 times 1/2 a cubed. So that's going to give us 2/3, and everything cancels out, a cubed. And then this is the area inside the parabola, the area of this entire rectangle here. This entire rectangle here, a times a squared, the height of the thing. Well, this is just a cubed. You know, the area of the rectangle is a cubed, and the part inside the parabola, 2/3 a cubed. Cavalieri's calculation, the part underneath the parabola, 1/3 a cubed. Yeah, it adds up to a cubed. Yes, these answers are consistent with each other. This was known as the method of, what is this one? Infinitesimal? No, not infinitesimals. Indivisibles, I believe. Yes. This is the method of indivisibles. This was Cavalieri's concept. All right, so we see there's a bunch of ideas about how to do this leading up to the late 1600s, right around 1700, maybe a little bit earlier than that, when Isaac Newton and simultaneously, independently, Gottfried Leibniz on the continent. He's German. Newton was English. They independently developed the idea of the calculus. Well, what is the idea of the calculus? In my mind, it's very similar to an idea that we see in trigonometry. And in trigonometry, we want to analyze some triangle, and we know that, first of all, the similar triangles have the same angles but different on the sides. So we're going to just analyze them with their angles, and that means we'll just be able to compute the ratio of the sides, because the absolute value of the sides varies. But we can certainly, based on the angles, we should be able to know what the ratio of the sides is. But then we say, well, ratio of what angle? I mean, we know that the angles inside the triangle add up to 180 degrees. Okay, so if we know two of them, that fixes the third one. But how do we, what do we have now? We have a function of like two angles, and we know that the third one is 180 degrees minus the first two. I mean, maybe, but that's kind of complicated. And we found a really brilliant, I'd say, simplification of that, and that is, let's restrict our attention to right triangles. And to me, this is the essence of math. This is the brilliance of mathematics. All right, so this one's going to be 90 degrees. We're going to fix this one, and we know that they add up to 180, so that means that this one must be 90 degrees minus. And in fact, now, okay, so we can set all these ratios as just a function of a single variable. Sine, for example, is going to be the opposite over the hypotenuse. So this would be the opposite. This would be the hypotenuse. That's an O, not a 0. And right there, so we have all of our ratios here just as a function of a single angle. That's nice, but apparently kind of restrictive because we're only looking at right triangles. But then we go a little bit further and we realize that we have, for arbitrary triangles, we have the law of sines, and we have the law of cosines, essentially. Well, we do. It's called the law. So, we have this law of sines. This works now for, this is the angle, say A, and this is the length A, and this would be the angle B and the length B. The same thing for C. This works for any, we're using, and then of course the law of cosines is going to be C squared equals A squared plus B squared minus 2AB cosine the angle C. A generalization of the Pythagorean theorem. But the real point I'm trying to make is this idea of restricting to a right triangle at first appears too restrictive to let us analyze arbitrary triangles, but in fact the tools we develop with right triangles then generalize to arbitrary triangles, and because we're only working with a function of a single variable, it is a massive simplification that is at the absolute core of modern trigonometry. Newton and Leibniz realized something similar with calculus. Because we're going to vary some. We're going to have derivatives. We're going to have integrals. When you go back to these these principles, these ideas that Euclid and Archimedes were using, how do we vary? This circle, this parabola, this breaking this thing down into smaller and smaller pieces. Function of what? You'd say. Well, this was the idea of the calculus. We're going to restrict to a particular shape. We're going to have a shape that is straight lines on three sides, and then on the fourth side we're going to add a function. So we're going to have a function of x here, and then we're going to have two boundaries here. And now we're going to let this right-hand boundary shift around. We have the area under here, and as we shift B around this area, now we get an area which is a function of the changing value of B. The question is, what is the relationship between A and F? And the answer is that as you say increase B a little bit, you're going to add one of these little strips of area, and the size of this strip is directly proportional to F. So the rate of change, the derivative of the area with respect to the position of this right-hand boundary, is f of x. And here we have basically half of the fundamental theorem of calculus, and this is the crucial simplification. We're going to restrict our attention to a shape with three sides, three straight lines, one function on the fourth side, and now we can let the position of the one side vary. And even though it seems kind of restrictive, really it's not, because there's a whole lot of shapes, like a circle, for example. You can just cut it in half and use the whole straight line segments to get the area of half the circle, and then once you know half the circle, you can get the other half. You have some more bizarre, complicated shape here. We can partition this thing into pieces, any one of which we can just use straight lines, and only one side varies as a function. So we're able to compute a pretty broad class of areas by restricting to shapes that have three straight lines on three sides, and then the fourth side is a function. That gives us this relationship between area and slope, and derivative and integral, and that is turns out to be absolutely that's it. That's the core of the calculus, is this is this relationship here. Because what this lets us do now is we can compute areas, integrals, using derivatives, and even though the two are dual to each other, the fundamental theorem of calculus tells us that the integration and differentiation are just dual operations. Realistically, practically speaking, it's far easier to construct derivatives than it is to construct integrals. So we just go and kind of differentiate everything in sight, get a table of derivatives, and then just flip the columns, practically speaking, and now get a table of integrals. And then that leads to, some of the results of calculus, like we've seen that, like this, the area under a parabola, well, this has been, as we see, basically known since antiquity. That's the the 1/3 a cubed that we just calculated a few minutes ago with Cavalieri's method. Oh, but then you do something like this, and this turns out to be the area. And I think something like this was just totally unexpected. Like so now we we were to plot this. Say just what are we going to do here? Is this like this hat function here? This is the 1 over x squared plus 1, and if we go from -1 to 1, you can compute this area in here, and it's going to be, well, the arctan of -1 is pi over arctan of 1 is pi over 4, the arctan of -1 is negative pi over 4. So we conclude that the area under this shape is pi over 2. And not only is it unexpected and surprising and a spectacular result of the calculus in 1700, but it can be verified. You can approximate this thing just by constructing polygons on this thing, and constructing the polygons and computing the areas. And as it gets denser and denser and denser, as you use more and more points to construct these polygons, your answer will be closer and closer to pi over 2. So it can be verified. Yeah, in fact, the area under this curve is the arctangent of x, which is like, where the heck did that come from? And I think those are the kinds of results of the calculus that really just established that it was it was real, it worked, it was here to stay. It didn't stop people like, is this the analyst, this Berkeley? Yeah, this didn't stop people like George Berkeley from criticizing it. He famously talks about these infinitesimals. They're neither finite nor infinitely small. May we not call them the ghosts of departed quantities. It was, again, he did not dispute the results of the calculus. The results are true. The question is, how do you make it rigorous? That was going to take another 150 years. Something else that arose from Newton and Leibniz was a controversy over notation. They each used different notation, and then mathematicians took sides in this fight, typically the English with Newton, who preferred something like y dot to indicate the derivative of y, and Leibniz, if I get his name spelled right here, Gottfried Wilhelm Leibniz. His preferred notation was this, and they feuded for years over what was the preferred notation. 20th century we developed jet notation. This to me is the resolution to this particular debate. And then jet notation is very common in PDE theory. We have, oops, I'm going to take that much away. Try it again. Y sub x. So it's almost as compact as Newton's notation. Leibniz's notation is, of course, bulkier, and it clearly indicates what the variable of differentiation is, which is the disadvantage of Newton's method. So, y sub x, I would say that is the, for me at least, in modern notation, it's jet is preferred over both Newton and Leibniz, and it's not worth squabbling over. Anyway, the especially when, okay, let's actually step to We'll come back to improper integrals. First, we'll talk about Cauchy. Now we're in the the early 1800s. He introduces the concept of a limit. How do we compute something like a derivative? Let's say f of x is x squared, and we want to compute its derivative. So we're going to do f of x plus h minus f of x over h. We're going to get x squared plus 2xh plus h squared minus x squared over h. This is we're going to cancel the 2x squareds out. We're going to get 2xh plus h squared over h. Divide out the h. And now we say we let h go to 0, so this just becomes 2x. And this is the kind of stuff that Berkeley is complaining about. I mean, can you divide by, is h 0 or not? Can you divide by 0 or not? I mean, if it is 0, then you can't divide by 0. Or can you? And Cauchy resolved this, and that is the way the derivative, the derivative, really by definition at this point, this is the limit as h approaches 0, the limit as h approaches 0, the limit as h approaches 0, the limit as h approaches 0 here as well, and now we use a theorem that tells us that polynomials are continuous. Continuity means if it's continuous, then it equals a function is continuous at a point if the limit as it approaches that point is the function itself. So we now say that because polynomials are continuous, we can actually set h equal to 0, drop the limit, and conclude that it is in fact two-way. I say drop the limit. We evaluate the limit by now saying, I should put on here, this one is still a limit. This one is still a limit as h equals 0. And now when we evaluate the limit, and we couldn't do this before because rational functions are not necessarily continuous. Once we get to a polynomial, the polynomial is continuous. That is a theorem. We apply the theorem. We can just set a, because the polynomial, now we can just set h equal to 0 and get 2x. That was the contribution of Cauchy, the concept of a limit. Now we're early 1800s. So like I said, it took about easily 100 years to get to this point from Newton and Leibnitz. And then Riemann, by the mid-18, died in 1866, so we're talking about like 1850s era now. He introduces the concept of a Riemann integral, which uses the limit. Uses the limit. And now what we're going to do is we're going to take our function and we're going to slice this up into rectangles, and we're going to keep subdividing it to smaller and smaller rectangles. We're going to compute an inner Riemann sum and an outer Riemann. These are now inscribed polygons. And then we're going to construct also an outer Riemann sum here. And as we refine this partition to be finer and finer and finer, we're going to ask ourselves, do the sums of the areas of these inner inscribed rectangular strips approach a particular limiting value? Now we have a well-defined concept of what that means to have a limiting value. And if the circumscribed rectangular strips also approach that value, then we say this has to be the area of the shape. So and to see, this goes back to Euclid. I mean, the same ideas that we have inscribed polygons, circumscribed polygons. We're refining them and refining them and refining them, and if both the inscribed ones and the circumscribed ones approach a single limiting value, that's the area. Well, this is Riemann's idea. It's just with Riemann now we have a more formalized concept of what it means to have a limit, so we can make this rigorous. And that's pretty much the way it is taught. I mean, we basically teach the Riemann integral in our math classes today. That doesn't mean there aren't issues with it. For example, improper. And there's always a chapter in an introductory calculus class on improper integrals. So here's an improper integral of the first kind. Let me zoom this in a little bit. An improper integral of the first kind, where we have the bound of integration going all the way up to infinity. So we have like an infinite sum, or the partitions now are infinite. And then here's one where we have a function that spikes up to infinity. And it would seem that some of these functions that spike up to infinity, can we evaluate them or not? I mean, we do something. Let's say the function is 1 over the square root of x. So it goes off, not very well sketched, but kind of like this. It goes off to, as we approach x approaches 0, it gets higher and higher and higher. And the question is, well, what is this area under here? We could simply just integrate the thing, because it's just x to the negative 1/2 power. So we're going to get 2 times the square root of x plus c. So this would suggest that we plug in x equals 0. This is 0, so we just plug in 1. This would be, it would seem, you would think that maybe 0 to 1, 1 over x dx, would be 2 times the square root of 1 minus 2 times the square root of 0, which is 0. So this would be 2, or is it? For the Riemann integral, strictly to note, this is not true for the Riemann integral. For the Riemann integral, the answer here is dne, does not exist. And the reason is because the Riemann integral, we have to construct this inner Riemann sum and this outer Riemann sum. How could you ever construct a outer Riemann sum around this part right here? There's always going to be, this left-hand partition is always going to be infinite. You can never circumscribe it with a rectangle. No, you cannot meaningfully construct an upper Riemann sum here. The upper Riemann sum just doesn't exist. That means, as in the Riemann theory, no, this integral does not exist. What they teach you in the calculus books is that we're going to do an improper integral, which we're going to do this. We're going to do, right? And then this thing is going to be the limit as a goes to 0 of 1 over the square root, or it's going to be 2 times the square root of x. So it's going to be 2 times the square root of 1 minus 2 times the square root of a. And that is, in fact, let's change this to make this red. It is, in fact, the area like in here, if that is a. And then we say, well, what is the limit as a goes to 0? Well, that then is 2. But strictly speaking, the limit with a bound of 0 does not exist, where you can do this construction where we construct this, we pick an arbitrary number, a, and then let a go to 0. Now we can construct this integral. This is the classic construction of an improper integral. So, I mean, there are aspects of this Riemann integral that are a little bit flaky here, but you wouldn't think that we're going to just like throw the whole thing out and replace it with something else, but really that is exactly what we did around early 20th century. Henri Lebesgue develops what we call the Lebesgue integral today. 1902, I think, is when he published his thesis, and a generalization of the concept of integration. And really, this theory has become dominant in 20th century mathematics. Most professional mathematicians today use the Lebesgue integral and not the Riemann integral. To explain the Lebesgue integral, I think we need to step back a few years, a decade or so, to the work of Cantor. Cantor, who played a pivotal role in the creation of set theory, most mostly related to our concepts of infinity. Cantor identified, the different kinds of infinity, and the ones we're most particularly interested are countable versus uncountable. A countable set is finite, but it can also be infinite if it can be made in a one-to-one correspondence with the natural number. So we can just count it, 1, 2, 3, 4, 5. And surprisingly enough, the the rational numbers are countable. If we were to construct a chart here, and imagine the chart just keeps going, and now in each one we do 1/2, 1/3, 1/4, 1/5, and now we're going to go 2/1, 2/2, 2/3, 2/4, 2/5. Right? So these are, if I extend this chart infinitely in both directions, I see I am going to get all of my rational numbers. And the thing is, I can count them. Now I can assign, I can see this one is number 1, this one is number 2, this one is number 3, this one is number 4. This one is actually identical. 1/1 and 2/2 are identical, so we can skip this one. This one is number 5. This one is number 6. This one is 9. I can keep going, running this diagonal argument here, 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 and I can actually count all of the rational numbers. I can just set up a mapping between the integers, the positive integers, and the rational numbers. So rational numbers are countable, but real numbers are not. The entire real line, the continuum as we call it, these are not countable. If they were, let's say we could, enumerate all of the real numbers, and it would be, let's say the real numbers between 0 and 1, and it would be something like point something or other, right? I'm not sure if it's a 3 or a 5, and this would be something else, and this would be something else. Okay, and now what I can do is I'm going to argue, I'm now going to construct yet another number which is different from number 1 in the first digit. So let's make it 2. And it's different from number 2 in the second digit. Let's make that 7. And it's different from number 3 in the third digit. Let's make that 5. And so on and so forth. And yes, I can construct a real number that is different from every one of these numbers in at least one decimal place, so therefore it is different. So I cannot count the real numbers. That the real numbers are uncountable, the rational numbers are countable. And it was these ideas that Lebesgue used to develop his theory of integration. This isn't exactly the way he developed it, but this is the way I think about it. Let's say we want to compute the area of some shape on the plane. And we want to do it by adding up all, let's just say we just, all the points, we consider all the points, infinite number of them, all the points inside this shape. And we add up their areas, and it's going to be, well, the area of a point is 0, so it's 0 plus 0 plus 0 plus 0 plus 0, and I guess we conclude then that the total area is 0. Well, that doesn't really work. That doesn't really make much sense. Doesn't seem like a very good idea. And what Lebesgue realized is actually this is a really good idea. We just need to identify the problem with it. The problem with it is that there are an uncountable number of these points. So it's even a question, how do you construct an uncountable sum? I mean, we could number all the summons in this sum. We can number them 1, 2, 3, 4. So this would be like a countable selection of points. How do we construct a countable sum from an uncountable collection? I guess we can just take a whole bunch and we could try, this collection of points or that collection of points, or another collection of points, and they're all going to add up to 0, but none of them really give us what we want because there's just too many of these points. There's an uncountable number of points. And what Lebesgue said is, what if instead, what if we just say we can't do this with uncountable sums? We have to use countable sums. We can do this, but if we have to use a shape here that has, a non-zero area, and we add another shape here, and we add shape here, and we add a 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 shape here, and we can add all of these things up, whatever their areas are, and we can total this up, and we can get to the total area here of this shape, as long as we make sure that the sum is countable. It's a countable sum, not an uncountable sum. And that turns out to, first of all, the Lebesgue integral is a superset of the Riemann integral. Let's consider our Riemann integral. Maybe make a little bit of a sharper curve here like this. So we're going to partition our Riemann partition here. Right, and this is our inner Riemann sum. And now as we want to partition this thing further, I'm going to split this one in half and split this one in half. All I have to do is add another rectangle right here and another rectangle right here, right? So I've got these original rectangles, 1, 2, 3, 4, and then I can, refine it by adding 1, 2, 3, 4, and then I could refine it further by adding 1, 2, 3, 4, 5, 6, 7, 8, or really I mean like 5, 6, 7, 8, 9, 10, 11, 12. Now I can actually construct the Riemann partition by a countable sum of these rectangles, but I'm always adding like smaller and smaller little rectangles to build up the Riemann sum. And yeah, I can construct a Riemann sum in the Lebesgue way, and that's how ultimately you can show that any function that is Riemann integrable is also Lebesgue integrable. So why then do mathematicians prefer the theory of Lebesgue? Well, for one thing, you get some very nice theorems that just don't hold, like the monotone convergence theorem that just doesn't hold. Let's see, we want the measure space. Yeah, so we have, this is all the language of the Lebesgue theory. We have a measure space, we have a pointwise non-decreasing sequence of measurable non-negative functions. Each one of the functions satisfies this particular condition here. So each k plus 1 is greater than or equal to k for all values of x. This is the key relationship. We have a whole series of these, a sequence of these things for all x. And then we're saying that if in fact they're all measurable, meaning they all have a Lebesgue integral, then in fact the limit, essentially the supremum of the integrals is equal to the supremum of the function f, or the limiting function itself. I don't quite see it here, but the function that limits. Yeah, here it is. The limit of the pointwise limit of all the functions. Its integral is equal to the limit of the integral of all the functions. So what does that mean? Let's go back to this example here where we're looking at 1 over the square root of x. And I can construct this as a series of monotonely increasing functions. I'm going to say for each one, I'm going to say f of k is going to be equal to 1 over the square root of x if x is greater than 1 over k, and it's going to be 0 for x less than or equal to 1 over k. So as k at 1/2, for example, is going to be this would be f2. It would be 0 here, and then it jumps up here and it comes down here. And then for, let's say, f4, going to go now to 1/4. This one's going to presumably come up to like here. And then it's going to be 0. And then it's going to jump up here. And it's going to, you know, for the part up here above, you know, 1/2, they're going to coincide exactly. That's the less than or equal to part. And then in here, we see that the 4 is greater, F4 is greater than F2 in this region here. And we just keep having a little piece here that's 0. As I'm kind of sketching out here now what F8 would look like. And what the monotone convergence theorem says is that in this case, the integral of the limit of the limiting value of as k goes to 0, or k goes to infinity, of fk is going to be what? Well, it's going to be the integral of 1 over x from 0 to 1, right? And what he's saying is that this integral actually exists and is equal to the limiting value of all these individual functions that compose the sequence. Well, that is basically saying, we come back up to here, it's basically saying that this integral is not dne, and in fact in the Lebesgue theory it is not. This integral does exist in the Lebesgue theory, and in fact we don't need improper integrals at all. If we had anything like, I mean, the monotone convergence theorem for the Riemann integral, we wouldn't need improper integrals. We don't need improper integrals in the Lebesgue theory because of the monotone convergence theorem. The other nice theorem we've got, well, do I have, I'm missing a page here. Let's see, another one is the dominated convergence theorem. Dominated convergence is another very nice theorem that is true for the Lebesgue theory. Dominated convergence theorem. Yeah, here it is. We have, again, a limiting sequence of functions where all of them are dominated by a single other function. So this lets us compute things like we have a function x that is 0 if x is a rational number and 1 if x is an irrational number. And the rationals are dense, so there's just like a whole bunch of zeros. No matter how small you partition your real line, you're going to get a whole bunch of zeros here, interspersed with a whole bunch of ones, and you can never construct you can construct an upper sum and a lower sum, but they'll never match. You know, the circumscribed rectangular strips are always going to be up here to catch the ones, and then the inscribed rectangular strips all have to be down here to catch the zeros. So the upper sum and the lower sum are never going to match each other in the Riemann theory. Yet this function is not integrable, not Riemann integrable, but it is Lebesgue integrable. And the reason is because now we construct a series of f of x's where we can say something like 0 if x is in Q and the denominator, let's say n over d, that is x, if that's x, d is less than k. So we only construct our denominators up to 1/2, and then for f3 we only construct our denominators like 1/3 and 2/3, and for f4, I mean, it would be 0 if x is 1/4, 1/2, 3/4 x elsewise. Well, this one is just now it's just 1, except at a couple places where it is 0, and actually that one is integrable. It's both Riemann and Lebesgue integral. We can just ignore the isolated zeros and we conclude that the integral is 1 if we're going from 0 to 1. Of all of these functions, f4, f5, f6, f7, their integrals are all 1, and that ultimately lets us conclude that the integral of this f of x is in fact 1, which it is in the Lebesgue theory. So the Lebesgue theory lets us compute integrals of functions that are not integrable under the Riemann theory, and you kind of like wonder like why do we care? I certainly have had some comments when I gave this lecture 2 days ago that one of the professors thought certainly for probability theory, we really want to use Lebesgue's theory. Engineers, I'm thinking, really don't care about any of it. They're fine with thinking of area in kind of the way Newton and Leibniz thought about it. It's just this kind of the vague. It's just the area under a curve. It's just the area under a curve, and we run this area. A is just just the area under a curve. Mathematicians, if we're trying to prove theorems here, we need a definition. Like, how do we define the area under a curve? And that's what the integral does for us. It's really a tool, a strictly defined integral, like a Riemann integral, a Lebesgue integral. It's a tool for proving theorems. How can we make these kinds of concepts rigorous if we don't have a really solid definition of what the area under a curve is? That's what the integral does for us. I would say for, like I said, for engineers, it's not that big. It's just the area under a curve. For mathematicians, we talk about the Riemann integral, the Lebesgue integral, because we need to have a strict definition of what we're talking about when we say the area under a curve. Okay, so that's what we got from this guy Lebesgue in early, like I said, not 1902, early, and by the mid 20th century, his ideas had become ubiquitous and absolutely dominant in modern mathematics. A couple other dates I want to mention in 20th century development. Non-standard analysis originated in the early 1960s by the mathematician Abraham Robinson. He's talking about the idea of infinitely small or infinitesimal quantities seems to appeal naturally to our intuition, but how on earth do we nail it down? Let's see. Where should I put this? Let's look at the something like the chain rule. Let's say we have, z as a function of y, and y is a function of x, so certainly that means we can write z as a function of x like this, or we can just say it's basically h. It's the composition of, h is the composition of f and g. And now we have the chain rule, which says dz dx is equal to dy dx times, what's it going to be here, dz dy. That, this derivative here, basically the derivative of h, that's dz dx, is equal to dy dx, which is g times, the derivative of g is basically saying, derivative of h equals derivative of g times the derivative of f. That's basically what this says. Now, strictly speaking, the Riemann theory and the Lebesgue theory too, what this statement is, it is a statement of a relationship between three limits. That's what dy, something like dy dx is. It is the limit, it's a derivative, it's the limit as h approaches 0 of y of x plus h minus y of x over h. It's a limit. This is a limit. This is a limit. This is a limit. This is a theorem that relates three limits. But if you just look at the way it's written, it's actually using the Leibniz notation as I'm using now, the dy dx notation, it's very tempting. Well, just cancel dy dx and get dz. I mean, it just kind of seems like, it's really a useful mnemonic, but does it actually hold up? I mean, can you actually cancel these infinitesimal quantities? And really, this is what Abraham Robinson developed, was a theory that says, yes, actually you can do this. He developed a theory of the hyperreal number system. So we have the real line, and then we have infinitesimally close to zero, like a whole nother real line. And then on this one, infinitesimally close to zero here, a whole nother real line. And you can invert these things. So if you have some infinitesimal number e, 1 over e is going to be infinitesimally big. So you're going to have like a whole another whole real line up here. You have this whole telescoping series of, real lines and real lines and real lines, and this is called a hyperreal number system. It hasn't really caught on, but it's certainly an interesting idea, and I'm thinking that, there are some problems even with the Lebesgue integral may very well not be the final word in analysis. For example, it can handle an improper integral pretty well. Here's something it can't do very well. Let's say we have 1 over x. Let's say we have 1 over x, and it looks like this. And the integral here of, say, -1 to 1 of 1 over x dx, again, this does not exist in both the Riemann and the Lebesgue theory, because the Riemann theory, because of this infinite extent, and even in the Lebesgue theory, you would evaluate these two areas independently of each other and find that they're both infinite, and you can't just add and subtract infinities. What you can do is construct what's called the Cauchy principal value theorem, and this would be something like the limit as a goes to 0, and now we're going to put a can we cancel these infinities? Can we somehow cancel these infinities against each other? This is a Cauchy a to 1 of 1 over x dx plus the integral of -1 to -a 1 over x dx. And then this whole thing would in fact be 0. The infinities would cancel each other out. These two shapes are exactly the same as each other, just mirror images of each other, so they would cancel each other out and you would get 0. But how could you do this? I don't know. I would not be sure. Something like the hyperreal number system might be it might be possible to extend. This shows up in distribution theory. If this kind of integral, this isn't just like totally abstract thing as you're canceling these areas. No, sometimes you construct these integrals. You do want these areas to cancel with each other, and there might still be room for the development of a new integral sometime in the future. The final date I want to put on here is that of Robert Risch and the Risch algorithm. American mathematician Robert Henry Risch, who developed it in 1968. This comes now to a question we have hardly talked about at all, and that is, can you actually do one of these integrals? In the sense, can you actually write down a formula for it? It's all the stuff so far. A lot of it's existence type questions, but okay, I know I'm going to do 1 over. Let's not do that just yet. Let's just say 1 over x dx is equal to 1/2 x squared. Can I do this? Can I just actually convert some expression here to some expression there? Is there some algorithm that lets me convert from this one to this one? And of course, the first question is, what are the immiscible functions? We no longer want to just say functions. I mean, a function is just a mapping from a real number to real numbers, so that could be just about anything. We talk about elementary functions. Elementary functions include things like polynomials, rational functions, which are ratios of polynomials, trig functions, exponentials, logarithms, inverse trig functions, just about everything except absolute value. absolute value. We leave this out of the mix. This is another 1960s era theorem that if we put absolute value in the mix, the question of evaluating an expression and finding whether there is another elementary expression, it does this. Can you write the antiderivative as an elementary expression? If the absolute value is in the mix, this problem very quickly becomes undecidable. And we can prove that there can be no such algorithm that does this. The absolute value really does kind of mix things up a bit. But if you leave absolute value out of the mix, you just do polynomials, rational functions, trig, exponential, all your basic like high school functions. Robert Risch actually, gave us the final piece of how to do that. And when you think about it, this is something that we've been trying to do since the time of Isaac Newton, solve an integral. And it took another 300 years to do it. So that just gives you an idea of how difficult it is. The basic idea is to construct a series of extensions. We have exponential extensions, we have logarithmic extensions, and we have algebraic extensions. Algebraic extensions. Those are the only kinds we need. These three: logarithms, exponentials, and algebraics, meaning roots of polynomials. And then something like sine. How do we evaluate sine? We use probably Euler's identity that lets us write sine in terms of exponentials. Could be as long as we have exponentials, logarithms. Exponentials certainly let us do sines. Logarithms actually let us do inverse sines. Once you put complex numbers into the mix, we can do inverse sine. And then algebraics, that is if we want to do something like 1 over the square root of x dx. The reason we call it algebraic is because really our preferred way of doing this right now is y squared equals, y is the square root of x. You say y squared equals x, and we want to do this integral here. A curve defined by a polynomial is called an algebraic curve, and this is actually a very important simplification. We get rid of these roots and we write everything in terms of polynomials, and now it just becomes a question of but this really is the preferred way to do it. We know a lot about algebraic curves. We've studied a lot if we just have just a general polynomial that relates y and x with each other. A lot of work was done on this is the field of algebraic geometry. A lot of work was done on this in the mid 20th century, and it was absolutely out of that current of thought that Robert Risch in the late 1960s realized that there have been some fundamental studies done by some Japanese mathematicians in the mid 1960s, and it was Risch who realized that lets us put a key bound on a constant that until then we just didn't know how to bound the thing, and that was the final theoretical piece in coming up with what we today call the Risch algorithm, which is, I don't know if there's any examples here, it's a process for integrating elementary functions, for either finding an elementary, something like this, taking this thing and solving it and figuring out this. That is, a classic example of the application of the Risch algorithm. And it just, I actually know a fair amount about it, but what's most interesting to me there is that it is something that was not developed until 1968. It really shows you how difficult integration really is relative to differentiation. So that's it. That's my, sweeping view of 2,300 years of calculus from Euclid all the way forward to Risch, and we got a good dozen or so big name mathematicians in between. I might do a follow-up lecture. I was discussed this before. The natural follow-up to this one. This was the historical development of calculus. the logical follow-up lecture in my mind would be the pedagogical development of calculus. Now, how, what order do we teach this stuff in? What courses can you take? And it is not done historically. You don't study calculus by studying Euclid. So there's a whole different order of things that we use when we're out to actually teach it. And that might be a second lecture that I might do on this. But that's it. That's my quick 30,000 foot survey of 2,300 years of calculus.